Okay, so continuing on chapter 4, we just looked at ionic substances and dissolving them in water, and what we found was that ionic substances can be soluble, in which case they dissociate. When you have a solution of an ionic substance that is dissociated like this in water, so you have ions there, it conducts electricity and it's called a strong electrolyte. Now, of course, if an ionic substance isn't soluble in water, it's boring, so we don't care about it. Now let's start thinking also about covalent substances. Covalent substances, again, can be soluble or insoluble. If they're soluble, they dissolve, but they do not dissociate. So therefore, they're known as non-electrolytes. They do not conduct electricity. Again, you've got a lot of insoluble substances that are insoluble in water. They're very boring. But there is a type of covalent substance that kind of crosses this boundary here, and we introduced that earlier. They're acids, right? If you remember, acids are covalent substances, but at the level that we're looking at, behave like ionic substances in aqueous solution. Now we'll start off talking about so-called strong acids. If you remember, an acid back from our discussion previously can be considered to be H+ and anions. And so when we put these things in water and they behave as an ionic compound, that means that they're going to dissolve and dissociate into their ions. And so a strong acid is one that completely dissociates into the H+ ions and the anion, and so strong acids are, of course, strong electrolytes. There are not very many strong acids, and you absolutely have to know these, have to recognize them as strong acids. Most familiar, probably HCl in aqueous solution. Again, remember, if it's not in aqueous solution, it's not an acid. It's a covalent compound, hydrogen chloride. When it is in aqueous solution, it is an acid, and instead of hydrogen chloride, we call it hydrochloric acid. Just to emphasize that we get complete dissociation. If you have HCl in water, it's not HCl stuck together. It is completely dissociated into H+ ions and Cl- ions. HBr, again in aqueous solution, is not hydrogen bromide, it's hydrobromic acid. Again, complete dissociation, so it's not HBr, it's H+ and Br-. HI in aqueous solution is hydroiodic acid. Doesn't exist as HI, even though it's convenient to write it like that a lot of times. It dissociates completely into H+ and I-. Nitric acid, HNO3, H+ and the nitrate anion. HNO3 does not exist in solution, although we'll write it like that because it is H+ ions and nitrate ions. HClO4, perchloric acid, same thing, not HClO4 in solution, H+ and ClO4- ions. Now the sixth strong acid that you need to know is kind of a weird one. It's the extremely well-known H2SO4, sulfuric acid. And you'd say, well, this is going to dissociate in solution, completely dissociate as it is a strong electrolyte, but it does not split up completely to give you 2 H+ and 1 sulfate. The complete dissociation part of sulfuric acid is only for that first H+ to come off. So the strong acid part of sulfuric acid is H+ and HSO4- aqueous. Now we'll mention this again in the next slide. It's something we'll talk about extensively in later chapters. Now, of course, if an acid is not strong, that means it must be a weak acid. Weak acids are substances, they're acids again, they dissociate into H+ ions and their associated anion, but this dissociation is only partial. Now we're not going to, in chapter 4, get into the big nitty-gritty about what we mean by this partial reaction. Let's just take it that when you have a solution of a weak acid, it's not 100% dissociated, it's 3%, 1%, 8% dissociated, so you have the undissociated acid and the ions in solution. Because you've got ions in solution, it's an electrolyte. Because it's not complete dissociation, so you don't have as many ions as you would expect, we call these things weak electrolytes. Now there are hundreds of weak acids. We're just going to look at a few of these. HF, worthy of mentioning, because of course you would expect HF to be a strong acid, seeing as how F is in the same group as Cl, Br and I, and those acids are strong acids. But HF, or hydrofluoric acid, is a weak acid. So what that means is when we have HF in aqueous solution, some of it becomes H plus and F minus, but also a lot of it is still there as HF. So unlike the strong acids, and we only had the H plus and the anion, hydrofluoric acid, a weak acid, we've got the undissociated acid plus the dissociated ions. Okay, some other weak acids that you're going to see quite a lot. You have the most common carboxylic acids. The first one, formic acid. Again, if you remember, this CO2H is indicative of an acid group, H being the simplest thing you can have with that. So formic acid or methanoic acid is the simplest carboxylic acid. When we look at that in solution, some of it does indeed split up into H plus ions and formate anions, but you also have a considerable amount of the undissociated formic acid. Next, and by far the more common in terms of our questions, carboxylic acid is CH3CO2H, again as the acid group. Now you've got the carbon CH3 instead of an H. So this is acetic acid, or of course systematically should be ethanoic acid, as you have the two carbons there in aqueous solution. It somewhat dissociates, so you have the H plus and the acetate, but of course you also have undissociated acetic acid there. One that you're very familiar with is H3PO4, phosphoric acid. This is what of course is in Coca-Cola. This is a very, very complicated system. As far as we're going to be concerned in this class though, even though it has three H's there, its main thing when you put it in solution, it's a weak acid, so you have H3PO4, and then you have some H plus and some H2PO4 minus. In other words, the anion, the dihydrogen phosphate anion that you get when you just take one of those H pluses away. A lot of books say there are 7 strong acids. There's actually dozens of strong acids, but in terms of freshman chemistry we don't get into what are called these super acids and so forth. But a lot of books say that HClO3 or chloric acid is also a strong acid. It's not for the purposes of this class. It's a weak acid. We'll discuss why when we get into chapter 18, those of you who are still with us there. So that means in solution you're going to have HClO3 and of course H plus and ClO3 minus. And before I move away from weak acids, let me return to the point made on the previous slide. Sulfuric acid strongly completely splits up into H plus and the HSO4 minus. Well, this HSO4 minus has an H there. It can act as an acid in its own right. Although this species, bisulfate or hydrogen sulfate, is a weak acid. So that means that if you have bisulfate in solution, you not only have the HSO4 minus in solution, you also have H plus and the sulfate. Now, of course, there's a word that always goes along with acid, and that word is bases. Bases are more complicated. We're just going to scratch the surface of the bases. We're going to make a couple of really weenie assumptions that we really have no right to make, but we can make it at this stage as long as we correct ourselves when we get to chapter 18. For us, what a base is it is something that dissociates in water to produce OH minus, right? And of course, if you're making OH minus, you're also going to have a cation. You can have strong bases. These are ones that completely dissociate and so therefore are strong electrolytes. And the ones that I expect you to know here are, and I'm not going to dwell too much on these because they're all things that you're very familiar with, LiOH, lithium hydroxide. You take lithium hydroxide in water, it's an ionic compound. We've already seen it as an ionic compound, and so we know that it is going to completely dissociate to Li plus and OH minus. Notice I haven't written any of the LiOH left. Of course, if lithium hydroxide is, sodium hydroxide is, again, NaOH, complete dissociation is Na plus OH minus. KOH, potassium hydroxide, complete dissociation into K plus and OH minus. I could go on, rubidium hydroxide, cesium hydroxide, the other members of the alkali metals. We'll jump over to the alkaline earth metals, strontium hydroxide. Notice that there are two OHs in strontium hydroxide. It is a strong base, so as far as we're concerned in water, it is not SrOH2. It's strontium ions and, of course, two hydroxide ions. Only thing about that too, it's not saying it's this special new substance, it's just giving us the relative amounts. You're going to have twice as many hydroxide ions as you are strontium ions. And then strontium's friend, barium hydroxide, same idea. Barium hydroxide does not exist in aqueous solution. Instead, of course, it dissociates to Ba2+, and there's those two hydroxides. Now, those of you who've been matching this up with the book will know that the book also puts in calcium hydroxide. In this class, calcium hydroxide is absolutely not a strong base. We'll talk about the reasons for that in a later chapter. It is not a strong base. It is incorrect to call it one. Now, we do need to talk about a few other things associated with bases. I've just given you a list of the strong bases. Well, obviously, if there are strong bases, it's probably weak bases. Right? Weak bases with the same type definition as we saw for the weak acids. These are substances that only partially dissociate to produce OH minus in water, plus of course their cation. Some examples of weak bases, and you can't look too closely at these because it will confuse you, but ammonia, NH3, is a strong a weak base. Other metal hydroxides, calcium hydroxide, iron hydroxide, and so on, are weak bases. And other anions, and historically the ones that are particularly important in this regard are carbonate and bicarbonate. Now, a lot of times you will also see mentioned that metal oxides are basic, and that's true, because when you take a metal oxide, you dissolve it in water, it makes the metal hydroxide. So to say that metal oxides and metal hydroxides are basic is somewhat redundant. Okay, example of this would be, say, sodium oxide there. Put sodium oxide in water and it gives you the sodium hydroxide. So sodium oxide in water is basic because it gives you sodium hydroxide, which right there is going to give you the hydroxide ions. And then finally, a lot of times you hear the word alkali. It's an old word. It's the word that would match up with acids usually in elementary school, in everyday life. At this level, alkali and base are interchangeable words, okay, because we're focusing on bases in water producing OH minus ions, and that is what an alkali is. When we get into chapter 18, we'll talk about much more general and important definition of that word base. But right now, you hear somebody say alkali, you know exactly what it is. It's what you currently are thinking of as a base. Now, acids and bases have some important reactions. We're not going to talk about all of them here. We are going to mention a couple of them in the context of what we've already done. Because, of course, when we were talking about ionic substances, their fundamental reactions are double displacement reactions. Acids are covalent substances that behave like ionic substances in water. Bases are ionic substances, so therefore acids and bases in water will undergo double displacement reactions. And there are some extra little aspects of these double displacement reactions that we'll have fun studying. The most important reaction of acids and bases is a so-called neutralization reaction. An acid is neutralized by a base so that neither have their acidic or basic properties anymore. Sure, back in pre-kindergarten you had the nice standard neutralization reaction, acid plus base gives water plus salt. Well, this is a double displacement reaction. Let's look at that. An acid is an H plus accompanied by anions. We're not going to worry about whether it's 2 or 3 of the H pluses, right? Just its general form, H plus with an anion. A base, as we have seen, is a cation and OH minus. So when these two react with each other, you're going to get a double displacement reaction. Now, a little warning here. As I mentioned previously, you have got to watch these things as shows. You can't take them out and just look at the individual slides because you lose too much information. And this is one of those where you lose too much of that information. If you just look at what is about to happen and print it out, it's going to look totally silly. But when you do it properly, the H anion plus the cation OH, the acid plus the base, are going to undergo a double displacement reaction in which, of course, the ions swap around. So there we are. See that ion swapping around? So the OH went from being with the cation to being with the H+. The anion went from being with the H+ to being the cation. Okay? This is the neutralization reaction. There's your acid, there's your base, there's water, and salt. Salt is the old-fashioned name for an ionic compound. So sodium chloride is of course a salt, but as is every other ionic compound. So neutralization reaction is just very, very, very simply a double displacement reaction. The net ionic equation for a neutralization reaction, what's really important here is it's the H+ plus the OH- making water. And I discovered a new little trick to show you the water there. There's some other nice reactions of acids and bases that we can still think of as double displacement reactions and more. The big one of these are gas forming reactions, okay? And some of you are probably chuckling, haha, gas forming, you know, let's talk about alimentary processes and so on. Indeed, that's actually where the things that form gas, the reactions that form gas in your tummy, are acid-base reactions. For example, if you take an acid and you mix it with the bicarbonate anion, then the products of this are water and carbon dioxide. Let's look at an example of that. His favorite acid, HCl, was found in the stomach. Sodium bicarbonate is baking soda. Okay, and some of you know that if you take a solution of baking soda and drink it, it will neutralize what's going on in the tummy a little bit because that bicarbonate is basic, as I said a minute ago, and you burp because it makes CO2. But anyway, first of all, let's look at it in terms of being a double displacement reaction. Okay, you're going to get the cation of the first, H, goes with the anion of the second, HCO3-, so you make H2CO3, and then of course the cation from the second goes with the anion of the first, you make sodium chloride in aqueous solution. It's this substance here, carbonic acid, that is interesting. Carbonic acid is rather unstable, and it very, very quickly breaks apart to give you water and CO2. Okay, so the net ionic equation for this, again noticing now the Cl- is aqueous at the start, it's aqueous at the end. The sodium is aqueous at the start, it is aqueous at the end. So the net ionic equation is very simply H+ plus bicarbonate, HCO3- goes to H2O plus CO2. So more gas forming reactions, right? The equivalent of what we just saw with bicarbonate with carbonate. Here, as carbonate is a 2- anion, you write it with 2 protons in there. Again, you get as the net ionic equation water and CO2. Instead of carbonate, you can use sulfite. 2H plus SO3 2- goes to water and a very nasty gas SO2. And then in a similar nasty fashion, acids react with sulfide to make hydrogen sulfide gas. Absolutely horrible, yucky, going to kill you if you breathe it for a very short time indeed. Now all of these have been gas forming reactions of acids. As a very famous and diagnostic of a base gas forming reaction exemplified here, in which you have ammonium reacting with the base. So what we have here is, here's our base, sodium hydroxide. The hydroxide is the important part, ammonium chloride. Let's do a double displacement reaction here, and we get the ammonium hydroxide going with the sodium chloride. Ammonium hydroxide, a lot of times you'll actually see it written as the aqueous form of ammonia. It very, very easily and extensively breaks down to give you ammonia gas and water. Okay, so the net ionic equation for this one, hydroxide base plus ammonium, right? It's a test for the presence of bases there, gives you water and the easy to detect ammonia gas. As a last comment in this section, and this is something that can be discussed in chapter 3, it's pretty inappropriate to discuss it in both of these. This is this word titration. Now, a titration is a very general form of a reaction in which, instead of taking the two reactants and mixing them together immediately in all their quantities, you take one of the reactants and you add the other one to it bit by bit by bit, so you can follow the progress of the reaction. Okay, so for example, in an acid-base one, we could take a base and add it in little bits to an acid, or we could take a base solution and add to it little bits of acid. Okay, now a lot of times you don't necessarily follow the progress to see what's happening in the progress. What you do is you take one reactant and add the other one until the reaction is complete. This is a way to see how much of a reactant you actually have to add to the other one. Okay, when you get to that stage where the reaction is complete, it is known as the equivalence point, because you have added exactly the right amount of one reactant to be equivalent to the other reactant. A lot of times you need to detect this equivalence point, and you can do this using some property of the solution's color change. Acids and bases, you measure something called pH that I know you've all heard of, but we're not going to worry about defining until we get again into chapter 18. When you do have some property change, color change, pH change, whatever it might be, that indicates the equivalence point, you actually say that that color change occurs at the end point. And of course, what you want to do is you want to have it so that your end point and the equivalence point are really close to each other. The end point, what you can see; the equivalence point, the actually interesting bit. Now, as far as we're concerned in this chapter, next chapter, in this course, when we say we're doing a titration, it's just us saying, hey, we're going to take this reaction and we are going to do it completely.